100 MHz. And to control them, this, my friends, is my new Ultra cluster. It consists of 8192 RISC-V processors running at 100 MHz. And to control them, there are 256 even bigger cores with FPUs. It took me half a year to develop this, and this is only a fraction of its final form. Of course I messed up things in the process and almost lost my sanity. But here's the story from start to finish.
At that time I was playing with a rather new chip from WCH. The CH570 is around 13 cents, runs at 100 MHz, has a multiplier and 12 kilobytes of SRAM. It even has a native USB and a radio. I tried it on another project and it's even fast enough to generate a TV signal, so leave a sub to not miss that one. Anyways, I thought that would be a great replacement for the CH32V3 that I used before. More RAM, speed and a better instruction set. With this new opportunity, an idea emerged. What if I make a cluster with an MCU for each pixel on the screen? This is madness.
Dude. Anyone who can handle a chip like that can build a fucking miniature drone bomb. It's terrifying.
But if I can pull this off, I could beat Nvidia, and Jensen Huang has to acknowledge my superior engineering skills. Alright. Having a core per pixel of a proper resolution would be insanely expensive. But what if we take the good old QVGA as a benchmark? 2 to the power of 16 MCUs would be enough, and also the next logical step after my biggest cluster with 2 to the power of 8 cores so far. 65,536 times 13 cents per MCU would total in around $8,500. That sounds like it could fit in my budget, at least with my naive calculations at that time. I needed to be sure I can even get the MCUs in the quantities. So I met Patrick, the CTO of WCH, who was always supportive before. He not only assured me the quantities are available, but also offered his help providing 10,000 MCUs free of charge later on. That was amazing. I was pumped and started doing the planning quickly, figuring out that 65,000 is a quite big number. At this scale, everything starts to become a problem. Best example are the power demands. The MCUs alone need around 10 milliamps per core. That's a total of 650 amps at 3.3 volts. That's 2 kilowatts. The limits of a European outlet can provide about 3 kilowatts, so that was the absolute limit, including an RGB LED per MCU and any other losses along the way. You need to consider 99.9% of the power is converted to heat. Dissipating that heat will be challenging. So I thought immersion cooling might be a thing. So I started planning around that.
The maximum diameter of an acrylic container that you can purchase easily is half a meter. Making a mock-up in CAD, it turns out I can barely fit enough what I call blades in that size. Each of these blades would consist of 32 rows of 32 MCUs. That would be a total of 1024 little MCUs and 32 row controllers. In the past I had a lot of issues with my bus systems. This time I wanted to try SPI at the lowest levels, as these are implemented in hardware and wouldn't use any of the processing power. 32 MCUs on each SPI seemed to be a sweet spot. And I could also use a row controller that had 32 pins for individual chip selects. So the row controller can directly select the client it wants to communicate with. Traumatized from data line crosstalk and signal issues on my previous projects, I put more attention to routing and shielding of the data lines from any external interference. Using Altium Designer for this was very welcoming, as it allows to specify the stack up and define rules that automatically sets the trace widths, so the signals are impedance matched. Since I had to put so many lines in a very confined space, I used 6 layers for the first time. Messing with high-speed PCI Express lines on the M.2 project, I learned how important uninterrupted ground planes are. So I decided to put ground on the second and fifth layers, enclosing all signals on the 2 inner layers. To shield the signals completely, I put also ground between each individual signal and staggered the 2 signal layers. Now every signal is surrounded by ground. Not sure if it's a strip line or a coplanar waveguide or a weird hybrid. But I was able to fit all lines, although it was quite cramped in some sections. Of course I had to give each MCU an LED. This time I picked a simple RGB LED. Addressable ones are just too expensive at that scale. These little LEDs are 1 by 1 millimeter with a nice diffusing body. They are typically used for bigger display matrices. They have a common anode, which is the positive side, and a pin for each red, green and blue. So the MCU serves as the ground, if you will. Another crucial part of the design is the power distribution. I used the bottom layer for this, since the top and bottom layers have twice the copper thickness. Running the power for each column LED and MCUs worked well enough with the copper pore. To test things, I designed only a single row and wanted to just clone that for the whole blade once I'm sure it works. And that turned out to be a good decision. I ordered and bought the parts and assembled them in my lab to get quick results and be also able to test partial assemblies if needed. Okay, moment of truth. It worked well enough out to be a good decision. I ordered and bought the parts and assembled them in my lab to get quick results and be also able to test partial assemblies if needed. Okay, moment of truth. Haha, yeah. Oh, cool. Oha. To save costs on 65,536 crystals, I thought I can simply provide a 32 MHz clock from a PWM pin of the Rogue controller. 8 MHz, 8 MHz, yes. I noticed the clock signal was really disintegrating at faster speeds. That must have been caused by the MCUs on the clock line, because the same clock on the SPI lines looked perfect. Even with the weird clock, I was able to program the little MCU. Yes. It's very dim. I can see the red very dimly. Oh, yeah, this is bright enough. The LED was working fine with the PWM, even with 1K ohm current limiting resistors. I was really thrilled to see it coming alive. Yeah! But then the problems started. Some of the MCUs refused to boot at all, and others stopped working.
But why is this? This is our initial one.
Strangely, touching the MCU made it boot.
Huh?
I simply had to switch the MCU clock source to bypass mode for the external clock source. Working with CH32V MCUs before, I knew the reference manual from the back of my head. But to my shock, on checking the clock section of the CH570 series, that option wasn't offered. Not only that, the clock pins have a maximum rating of 1.4 volts. No wonder the clock signal was chopped to pieces. There seemed to be no way around the crystals. I assembled a board with a single MCU and crystal in deadbug mode.
Right, let's add the jumpers. This is little MCU.
And that worked.
Woo. And this is Biggie. Whoop.
That mistake set me off a few weeks for a redesign and another spin of the test board. Fitting an additional crystal footprint in that already cramped design was really challenging. The new test board arrived and the MCUs worked finally.
Oh yes, okay.
I didn't waste any time and finished the design of the blade. And that's where we started to hit the limits. The complexity of the finished design just overwhelmed the server of the manufacturer. Over 10,000 vias and 5,000 components per board couldn't be handled. I had to divert from my original plan and split the blades. Two boards side by side were not seamless anymore, but they would barely fit in a planned container. I also had to pivot to smaller PCI Express connectors for the interface and reorder those parts. Uploading these Gerbers worked finally. As a test, I ordered only 4 assembled boards and 1 bare PCB for a little fee of 400 euros including shipping.